this breadth first search algorithm last time, and we are about to look at that bipartite graph. So let us again look at the definition of a bipartite graph, and we'll go through an example to decide whether a graph is bipartite or not, and then how to find out the two partitions. Okay, so graph is said to be bipartite if you can partition the vertices in the graph into two sets, such that each vertex is in one of the sets. So like you have a graph of 8 vertices here, and you could partition this into two sets of 4 vertices. Now again, the partition need not be of the same size. One partition could be just 2 vertices, the other partition could be 6 vertices. That is also possible. So just in this example, it comes out to be both the partitions have the same number of vertices. Now this is the main requirement you need to have. That is, all the edges in the graph should be between vertices across the two partitions, and there should not be any edge between vertices in the same partition. If you have something, if you satisfy this property, then a graph is said to be a bipartite graph. Okay, so what is the main requirement? All the edges should be between vertices across the two partitions, not within the same partition. That's what is the requirement for a bipartite graph. Now, if a graph is bipartite, we can also refer to it as two colorable. So two colorable means, so again, this is say the given graph, you want to color the end vertices of the edges such that for every edge, the two end vertices are of different color or of the two different colors. So if the graph is bipartite, you can see we can color the end vertices of each edge in such a way that the two end vertices for each edge are of the two different colors. Okay, so just color the vertices in one partition with one color and color the other vertices in the other partition with the other color. So that is what is a two colorable graph. So what we'll do now is go through an example for running breadth first search on a given graph, and then use the result of breadth first search to decide whether the graph is bipartite or not. So let us go through this example for breadth first search. So how you do breadth first search? Given a graph, you pick a starting vertex. Now it does not matter which starting vertex you pick. You could pick any vertex you want. So just as a convention, we will pick the vertex with a smaller ID as a starting vertex. Now when we do that, we also set these things. So if you go through the pseudocode of breadth first search, what we do is, once you pick the starting vertex, we add that vertex to the queue, as well as set its level number to 0 and set the level numbers of the other vertices to infinity, and also maintain a boolean flag for every vertex whether it is visited or not as part of breadth first search. So initially, for all the other vertices other than the source, the boolean flag is set to false, and only the starting vertex has been visited. So that's what we are having here. So we enqueue that vertex 1 to the queue, set its level number to 0, and set the level numbers of all the other vertices to infinity, and then also consider that vertex has been visited. So now go through the sequence of iterations. So in each iteration, what we do is we dequeue a vertex from the queue and explore its neighbors. So in this case, we dequeue vertex 1, which is the only vertex in the queue. So the queue temporarily becomes empty, but you're going to add the neighbors of 1 to the queue now. So you explore the neighbors of 1, which are 2, 3, and 7. Now none of these vertices have been yet visited, so we mark them as visited now. So when you visit a vertex for the first time, we also label that edge that you used to visit that vertex as a tree edge. So we call this edge 1, 3 as a tree edge, 1, 2 is a tree edge, 1, 7 is a tree edge. As well as you add these vertices that you visited to in the queue now, and then also set the level numbers of these vertices to be 1 more than the level number of the vertex you visit from. So The vertex that you visited, you explored is node 1, its level number is 0, so you set the level numbers of node 2 to be 1 more than that of node 1, so 0 plus 1. Similarly, 0 plus 1 for node 3 and 0 plus 1 for node 7. So these are the 4 things you need to do. So again, you can refer back to the pseudo code. Level number of, so once you explore a vertex, you set its level. So use the vertex to DQ, visit each neighbor V of U. If that neighbor V has not been yet visited, so if visited of V is false, level number of V is level number of U plus 1, visited of V is true, NQ node V to the Q, as well as label that edge UV as a tree edge. So these are the 4 things you do. Okay. So I think we are looking at example 2, so it's the same thing. So you add 2, 3, 7 to the Q. Okay. So now so this is the first iteration. So continue the iteration. So DQ the Q. So 2 comes out of the Q. So you're going to explore the neighbors of node 2. So the neighbors of node 2 are 4 and 8. Of course, 1 is also a neighbor, but 1 has been visited already. So that's why we don't consider 1 now. So we just look at the neighbors that have not been yet visited. Now, and also you see the edge to 1 has been classified as a tree edge. So there's nothing that we have to do with neighbor 1. So the neighbors that you have to look at now for node 2 are 4 and 8. So what are the things we need to do? We need to mark those 2 neighbors as visited. So we color them here and make them as visited and set their level numbers to be 1 more than the level number of node 2. So it's 1 plus 1, so that is 2 for each of nodes 4 and 8. And then mark those edges as tree edges because they are used to visit these vertices for the first time. So label them as tree edge 2, 4 and 2, 8. As well as add 4 and 8 to the queue. So 2 has been just removed from the queue, so the queue temporarily has 3 and 7. So now you add 4 and 8. Now in what order you will add the neighbors of a vertex to a queue, it's up to you. You could add them in any order. So we'll just follow the convention of adding them in the order of their IDs. It doesn't really matter in what order you add them to the queue. So the queue currently now has 3, 7, 4 and 8. So now continue the iteration. So you DQ the queue, 3 comes out of the queue. So the neighbors of 3 are 1, 4 and 5. But if you look at it, the neighbor 1 has been already visited and that edge has also been already classified as a tree edge. So we need to look at neighbor 4, which is also visited. So but this edge has not been yet classified. So if you have an edge to a neighbor that is already visited, then you call that edge as a cross edge. So that's how just to differentiate from a tree edge, you can draw a cross edge like this with a dotted line. So that's all you need to do if that neighbor has been already visited. Just call that edge as a cross edge. Now neighbor 5 has not been yet visited, so we have to do those 4 things. First, mark that neighbor has been visited, and then label that edge to that neighbor as a tree edge, and then set its level number to 1 more than the level number of this vertex 3, so it's 1 plus 1, 2, as well as add 5 to the queue. So when you remove 3 from the queue currently has 7, 4 and 8. So now you add 5, so the queue becomes 7, 4, 8, 5. So now this is the queue at the end of this iteration. So now you again DQ the queue. So 7 comes out of the queue. Now if you look at node 7, it has 2 neighbors, 1 and 8. 1 is already visited and the edge is also classified as a tree edge. So we don't have to do anything with node 1. But this node 8, which is already also visited, so we have to just classify this edge. So that edge to a vertex that is already visited will be called a cross edge. So we don't have any neighbor of node 7 to add to the queue. So if you just remove node 7 and do this thing, so 4, 8, 5 will be the content of the queue now. So now you DQ the queue, so 4 comes out. So for node 4, we have 2, 3 and 6 as neighbors, but 2 and 3 already visited and the edge is also already classified. So you have to just deal with node 6. So we mark node 6 as now visited, and label this edge as a tree edge because visiting node 6 from node 4, and set the level number of node 6 to be 1 more than the level number of node 4, so it is 2 plus 1, so that's going to be 3. And also add node 6 to the queue, so the queue will temporarily have 8 and 5. Now you're adding node 6 to the queue. So now that is the fourth iteration. So now we are in this fifth iteration. So the fifth iteration will be dequeuing node the queue. So node 8 comes out of the queue, but the neighbors of node 8 are already classified. So that's the end of that iteration. We don't have to do anything in that iteration. So now the queue has just 5 and 6. So now we dequeue the queue, so 5 comes out. So you have for node 5, 3 and 6 as neighbors, but we already did everything that we need to do for node 3. We classified that edge as a tree edge and marked that a node has been visited. So only thing we have to do with node 6, which is also visited already. So we have to just classify this edge to a vertex that is already visited as a cross edge. So we do that, and so this is the queue now. So when you dequeue the queue, 6 comes out of the queue, but again all the neighbors of 6 are already visited and the edges are classified, so we don't have to do anything. So the queue becomes empty. So we started breadth first search from 1, and we are able to visit all the vertices, means we are able to mark them as visited. And there are no remaining vertices in the graph. So as I said last time, this itself can tell that the graph is connected. Means you started breadth first search from one vertex and you're able to visit all the vertices. So that means this is a connected graph. Now, what about the bipartite property? So the rule that we need to check for the bipartite property is this. If at all there is any cross edge in the graph, the end vertices of the cross edge should not be at the same level. So if at all there's a cross edge, there could be the end vertices could be at 2 different levels. So for all cross edge, this property should be satisfied. So let us check here. So for this cross edge, the 2 end vertices are at different levels, 1 and 2. So that is fine. Now for this cross edge, the 2 vertices are at different levels, 1 and 2. That is fine. This is also a cross edge where the 2 vertices are at different levels. So if there are cross edges, the end vertices of the cross edges should be at 2 different levels. They should not be at the same level. Now even for one cross edge, if the end vertices are at the same level, then that graph is not bipartite. So if you look at the result of the first example that we went through last time for breadth first search, this is the classification of the edges and the level numbers we ended up with. So if you look at, say, this cross edge between 2 and 7, both the end vertices 2 and 7 are the same level number 1. So the presence of such a cross edge, just this cross edge with the end vertices at the same level, will rule out this graph from being called bipartite. Okay, so that is how we decide whether a graph is bipartite or not. So now that we have decided that this graph that we just worked on is bipartite, we could go ahead and identify the 2 partitions of that graph that will form a bipartite graph. So the way you can identify the 2 partitions is this. Just put together the vertices with the even level numbers in one partition and the odd level numbers in the other partition. So even numbers means like including 0, we can say 0, 2, 4, all those are even numbers. So in this case 0 and 2 are the even levels we have. So the corresponding vertices are vertex 1, 5, 8 and 4. So 1, 5, 1, 4, 5, 8. So all these 4 vertices are ending up with even level numbers. And then 2, 3, 6, 7 are the vertices with the odd level numbers. So just put together the vertices with the even level numbers in one partition and the odd level numbers in the other partition. So that is the rule to identify the 2 partitions. So as you can realize by now, there could be that one partition has just say 1 vertex or just 2 vertices and the other partition has the remaining vertices. So that's possible. So it just depends on the level numbers of the vertices. Now, so once you identify the two partitions, you can draw the edges, just what you have in the graph. So all these edges I have drawn here are the edges here. So I have not drawn any new edge here. So let us check. So from vertex 1 you have an edge to 2, then 3 and 7. So you draw from 1 you can edge to 2, 1 to 3 and 1 to 7. Then from vertex 2 you have an edge to 4 and 8. So 2 has an edge to 4 and then an edge to 8. 3 has an edge to 1, 5 and 4. So already you had this edge 1, 3. So 3, 1, then 3, 4 and 3, 5. Similarly 4 has edge to 2, 3, 6. 4 has edge to 2, 2, 3, 2, 6. So you can cross check. All the edges that you have in this graph will be now edges that are between vertices in the two partitions. There will not be even a single edge between vertices in the same partition. So such a graph is now said to be bipartite. So we can then color the vertices such that all the vertices in one partition will be of one color and the other end partition they are different color. So for each edge the end vertices are of two different colors, because we are having only two colors and it is possible to color the end vertices of every edge with the two colors. So that's why in an exam I could ask you check whether this graph is two colorable or not. That means you have to really check whether the graph is bipartite or not and show the two partitions. Okay. So any question with this? How to check whether the graph is bipartite or not? Okay, you can type if you have any questions, or you can use a microphone to ask the question. Let me save this in the meantime.